my idea of a fourth quadrant events, and don't worry, I'm going to get back on asteroids here in just a second. But this is kind of a fun thing. This is going to take just a minute to play out. But this is a diagram that somebody put together recently that looks at the employment picture in the United States over the last few years. And at first it comes along, and it looks pretty normal and relatively healthy, and there's generally more green than red, and you know, it's the kind of thing we like. I mean, we have to create jobs all the time because there's more people, right? So anyway, it hums along, and then here, a little bit later in 2005, you're about to see Katrina. That would be Katrina. And then there's kind of an echo effect in Detroit afterward, probably because of the effect on fuel prices and car purchases and, you know, things like that happening. And then it just kind of hums along for a while. And then in 07, the green kind of starts to go away. And then we get into 08, and you start seeing a whole lot more red. And Glenn Reynolds, who linked to this out on Instafund, which is how I got it, said this thing looks like some kind of a nuclear war simulation at the end. And there we go. Okay. Glad we're in one of the smaller red dots. Yeah, anyway, so four quadrants, black swans, scary stuff, generically. Let me try to get it back on track here. Okay, geopolitical risk, with apologies to Richard Feynman, who wrote a book with this title. The meaning of it all, asteroid size distribution and composition combined with terrestrial realities, such that rare larger impacts and frequent smaller impact ranges, and the tens of kilotons are usually airbursts, but so are nuclear weapons, and the explosions look exactly the same in a world of, I love the euphemism here, hostile capabilities among various actors with whom we have conflicting interests. Okay, more fun books. Now we get into the global catastrophic risks generically. Here's a good book that came out a few years ago. It's got a bunch of different essays in it. They're not all, the quality isn't uniformly high, but they're pretty good. And they categorize global catastrophic risks as falling into one of three types: risks from threats from nature, threats from hostile acts, threats from unintended consequences. And the kind of scenario I've been talking about is really the intersection of all three. Let's see here. And then another, let's see, did I get that? Yeah, I got that from the same book. Some really fancy phrases here. Observation, selection effects, and anthropic overconfidence bias. I think academics just sit around making stuff up like this. Because in plain language, all that adds up to is that just because something hasn't wiped us out yet doesn't mean it can't happen. Okay. When you look at this, the distribution of Earth-crossing objects is more important than the distribution of craters. The geologists finding the craters are important, but the astronomers finding the asteroids are really important. It's a difference between human history being affected by past impacts, some of the things I've talked about, and human history potentially being ended by one of these things hitting and, starting a nuclear war. So what do we do about it? Well, let's save civilization. Okay, and first, what not to do. This is probably the most important slide in the deck, so I'm actually going to read this. This is from a book called Global Catastrophes and Trends by a guy named Schmiel. He says, we should act incrementally as prudent risk minimizers and pursue any effective no regrets options. We do not have to wait for the formulation and acceptance of grand strategies, for the emergence of global consensual understanding, or for the universal adoption of more rational approaches. In other words, just start working on the problem, okay? Don't wait for everybody else to figure it out. So we got to find them first. And here are the detection efforts going on. These are all automated facilities. Most of them are in the southwestern United States. A few of them are scattered elsewhere around the world. It'd be nice if we had a few more in the southern hemisphere, but hey, you start with what you've got. And this is a lot more than we had just a few years ago. And once they've been detected, we start figuring out what the chance is that they're going to hit us. And that's where this Torino scale comes in. The short version of this is that 0 is a clean miss and 10 is everybody dies. As I mentioned earlier, the highest any asteroid has been on this is Apophis. It made it up to a 4 on the scale for a while. It was thought it would hit us on Friday the 13th of April 2029. And it would have been about a 2,200 megaton impact, so you wouldn't have wanted to be anywhere near that one. And indeed, some observations taken by the ASKC helped refine its orbit and determine it's actually going to miss us. And this is where those observations were made. I don't know how many of you have been out here. This is out in a city park in Lewisburg. This is a classroom. That's the big 30-inch Lucina telescope we'll talk a little bit more about in a minute. That and this telescope here, which has a special camera on it, are the ones we use for the asteroid work. And we have a 12.5-inch and a 16-inch here that are called the Lewisburg Community Telescope. And collectively, that's a roll-off roof here. Okay. All right, brag on the big telescope. This is the biggest one in 5 states that's open to the public. Really, the most important thing about it probably is the light grasp, because the illuminized area of the mirror is actually 29 inches across. It's gathering 11,000 times as much light as your eye. It can immediately go down to about magnitude 17. That's 20 times fainter than Pluto. We could see about 100 million stars with this thing, thousands of galaxies. We could see a star as bright as the sun, 8,000 light years away. And it pulls in so much light that it starts activating the cone cells in your retina, so you start seeing color in objects in the sky at night, which you normally cannot do. It is named for a man named Gary Rusinger. He was a machinist from Blue Springs. He worked on it every weekend for 1.5 years back in the 80s to get it built. I shudder to think what we would have had to pay for that kind of time that hadn't been donated. This is the telescope we do most of the asteroid work with, and we've got this shed there in back. You can see some of the guys at work. It's a 12-inch Cassegrainium reflector. It's pulling in about 1,800 times as much light as your eye, and in combination with a CCD imager, it can also go down to about 17th magnitude. It's 25,000 times fainter than the faintest star you can see with the unaided eye. Okay. And notice the thing it's in is this like disintegrating plywood thing. Well, we replaced that. And now it's in one of these, which is called a sky shade pod. And that guy there is Derek Gray, who is the director of Powell Observatory. His day job is teaching science to high schoolers out in the Great Pack district. Now here's an asteroid that we took some pictures of, and that I was able to get one of the guys, Dick Trenton, to give me the information on. It's called 2004 QT24. The date on here is April 22nd of 05, showing where it was in its orbit, because that's when these pictures I'm about to show you were taken. You can see it was just outside the Earth's orbit then. The distance looks like about 1/9 of an AU. Okay, so I don't know, 16, 17 million kilometers, something like that, maybe 50 times the distance to the moon. That MOID means minimum orbit intersection distance, which, as far as we know, this is as close as it can get now, which is about 3 times the distance to the moon. But we're keeping an eye on this one because it would be something like 23,000 megatons if it hit. Okay, here are a series of 3 pictures, and what I'm going to do is blink these. So let me just immediately go to the next slide. You want to look at that. Oops. You want to look at that. Okay. See the movement? Those are taken about 10 minutes apart. And that's how we find these. Clyde Tombaugh found Pluto the same way, except that he didn't have computers and software. He had physical glass photographic plates and some kind of mechanism that moved back and forth, and he had to sit at a desk and work on it for months, whereas we can do it in a few minutes. Which, by the way, is the real reason that Pluto is still a planet, as far as I'm concerned. Okay, so how do we save civilization?